From particles that communicate instantly across galaxies to the mind-bending reality of time dilation, quantum physics challenges everything we know about our universe. Join us as we explore these fascinating mysteries that exist at nature's smallest scale. Let's explore one of the weirdest features of quantum physics: quantum entanglement. Einstein called it spooky action at a distance, and it's easy to see why. When two particles become entangled, they form a special connection that stays linked no matter how far apart they are. Imagine you have two coins that always land on opposite sides. If one shows heads, the other always shows tails, even if they're on different planets. Scientists have actually tested this with particles separated by hundreds of miles. When they measure one particle, its partner instantly responds, seemingly breaking the rule that nothing can travel faster than light. This discovery has huge potential for future technology, from super-secure communications to quantum computers that could solve problems regular computers find impossible. Time isn't as simple as your clock ticking away at the same speed everywhere. Einstein showed us something amazing. Time actually moves differently depending on how fast you're moving or how close you are to a massive object. Think about this. If you were on a super-fast spaceship, time would actually move slower for you than for your friends back on Earth. This isn't science fiction. We've proven it with incredibly precise atomic clocks. Astronauts on the International Space Station actually age slightly slower than we do on Earth. GPS satellites have to account for this time difference to work properly, or they'd be off by miles. The closer you get to the speed of light, the more dramatic this effect becomes. If you could travel at 99.9% the speed of light, you might experience just a few years while centuries pass on Earth. Get ready for something that sounds impossible. Particles can actually pass through solid barriers. This weird behavior is called quantum tunneling, and it happens all the time in the quantum world. Think of it like this. If you throw a tennis ball at a brick wall, it bounces back. But at the quantum level, particles sometimes just pop through walls like they're not even there. It's as if you could occasionally walk straight through a closed door. This isn't just a cool trick. Quantum tunneling is essential for how our sun works, making nuclear fusion possible. It's also the reason some atoms naturally break down in radioactive decay. Modern technology uses this effect too. Flash memory in your phone and some types of microscopes rely on quantum tunneling to work. It's a perfect example of how the quantum world plays by completely different rules than our everyday experience. Now let's tackle one of the most famous thought experiments in physics, Schrödinger's cat. Imagine a cat in a sealed box with a device that might or might not kill it based on a random quantum event. According to quantum mechanics, until we open the box and look inside, the cat is both alive and dead at the same time. This might sound crazy, but it shows us something important about quantum particles. They can exist in multiple states at once, called superposition. It's like having a coin that's both heads and tails until you look at it. Scientists use this principle in quantum computers, where quantum bits can be 0 and 1 at the same time, making them much more powerful than regular computers. Here's a mind-blowing idea that's gaining attention in physics. Our entire universe might be like a giant hologram. The holographic universe theory suggests that everything we see in 3D might actually be information stored on a 2D surface, like how a credit card hologram shows a 3D image from a flat surface. This idea came from studying black holes, where scientists found that all the information about what falls into them seems to be stored on their surface. Some physicists think this same principle might apply to our whole universe. Think about watching a 3D movie. The screen is flat, but you see a full three-dimensional world. Similarly, what we experience as space, time, and matter might be projections of information stored on some distant cosmic surface. While this might sound like science fiction, serious scientists are testing this theory with complex mathematics and experiments. Get ready for one of the strangest experiments in physics, one that suggests our choices today might affect what happened in the past. In Wheeler's delayed choice experiment, scientists shoot particles of light through a special setup that tests if they behave like waves or particles. Here's the weird part. The decision about how to measure the light is made after it has already started its journey. Somehow, this later choice seems to determine how the light behaved earlier in its path. It's like deciding to watch a baseball game changes whether the pitcher threw a fastball or a curveball after the pitch was already thrown. This experiment has been done many times in labs, and it keeps showing this bizarre result. While it doesn't mean we can change history, it shows us that time in the quantum world works very differently than we thought. Space might seem smooth and empty, but zoom in far enough, we're talking way smaller than atoms, and it becomes a wild, bubbling mess. This is quantum foam, where space and time break down into a constantly changing landscape of tiny holes and bumps. At this super tiny scale, about 1 billion times smaller than an atom, the rules of physics go crazy. Energy pops in and out of existence, creating mini black holes that appear and vanish in an instant. Think of it like the surface of a calm lake. From far away it looks flat, but up close you see all the ripples and waves. Scientists think this foam-like structure might be the basic building block of space itself. While we can't see quantum foam directly, its effects might help explain some of the universe's biggest mysteries. The double-slit experiment is the perfect example of how weird quantum physics can be. When scientists shoot tiny particles like electrons through two slits, something amazing happens. Instead of making two lines on the detector screen, the particles create a pattern that looks like ripples in a pond. It's as if each particle goes through both slits at once, like a wave. But here's where it gets really strange. If we try to watch which slit the particle goes through, it suddenly acts like a normal particle and just makes two lines. By simply observing it, we change how it behaves. This experiment shows us that at the quantum level, particles can act like both waves and solid objects, depending on whether we're watching them or not. Let's explore quantum teleportation, but don't expect Star Trek-style transportation just yet. What scientists can actually teleport is information about quantum states from one particle to another. Here's how it works. Using quantum entanglement, researchers can transfer the exact properties of one particle to another particle far away. While we can't beam people across space, this technology is already being used to create super-secure communication networks. China has even teleported quantum information between Earth and a satellite. Scientists have successfully teleported information across cities and are working on building quantum networks that could form an unhackable internet. The cool part is that the information doesn't travel through the space between points. It appears instantly at its destination. Let's explore one of quantum physics' most puzzling ideas, the observer effect. When scientists look at tiny particles, something strange happens. The very act of measuring them changes their behavior. It's not about fancy equipment disturbing these particles. It's the measurement itself that causes the change. Imagine a shy friend who acts totally different when they know someone's watching them. Similarly, particles exist in multiple possible states until we observe them. Then they pick just one state. This has led some scientists to wonder if consciousness itself plays a role in shaping reality. While this idea is controversial, experiments keep showing that the quantum world behaves differently when measured versus when left alone. Thanks for joining us on this quantum journey through the universe's strangest mysteries. If you enjoyed exploring these mind-bending concepts, hit that like button and subscribe for more fascinating science explained simply. Share with friends who love learning.